Every time you refresh a web page, every time a game generates a random map, every time a bank runs a risk model, somewhere a computer is generating numbers that appear random, but are not. These are pseudo-random numbers, deterministic sequences that pass statistical tests for randomness. And in the world of simulation, they are the raw material from which we build entire virtual realities. In this documentary, we explore one of the most fundamental tools in simulation science, the exponential distribution. We will see how a simple integer seed, a single number, transforms into a sequence of values that can occur only moral the chaos of a real hospital emergency room. The pipeline is elegant, starting from a seed tree, we generate a uniform pseudo-random number array between 0 and 1. Then, using a mathematical transformation, we convert array into me, a sample from the exponential distribution. This is the journey we will take today, from seeds to randomness to simulation.
Hi, I am STEFANNY ARIAS. In this section, I want to tell you why we choose exponential distribution to model something as real and urgent as patient arrivals at a hospital emergency department. Let's imagine the emergency room of a hospital, here in Tunja, in Bogota, or in any city in Colombia, Latin America, or Exponential. The patients don't arrive in an orderly line or at fixed times. Suddenly, a motorcycle accident brings in two people. At almost the same time, an elderly woman appears with severe chest pain, followed by a child with a high fever, after hours of calm. These arrivals are unpredictable, but during specific time slot, especially at peak hours. They occur continuously, independently, and at an average rate that remains relatively constant. Studies in emergency departments, both in public and private hospitals in our region and around the world, show that the times between patient arrivals closely follow an exponential distribution. Why? Because each arrival is a magnetic event. The probability of someone arriving in the next minute is the same, regardless of whether 30 seconds or 10 minutes have passed since the last patient. This memoryless property makes the exponential ideal for this process. Event series such as the time zone capture that sense of chaos in emergencies, where anything can happen suddenly. In our documentary, we use a lambda rate equal to 0.25 patients per minute. That means that, on average, one patient arrives every 4 minutes, a moderate but safe pace, typical of many emergencies in our country during day or night shifts, without reaching total collapse. Why is it so powerful to generate the samples in simulation? Because with the arrival times we will obtain, the ends of values we will see in the practical demonstration, we can construct a complete and realistic timeline. To know exactly when each patient arrives, accumulate weight in the waiting queue, coming same with core times, which we also model as exponential, and calculate key indicators used by hospital administrators, the average waiting time for patients, the maximum length of the queue, the percentages of time the doctor or nurse is passing, or where it's necessary to open another threat room or asking more staff at certain times. In real life, the simulation models help make concrete decisions that save time, resources, and above all, improve care. How many doctors to assign per shift? Where to invest in more observation beds? Or how to reorganize the flow to reduce those wise diets sometimes exceed 30 or 60 minutes and cause a lot of stress for patients and families. Exponential distribution is not just a mathematical tool, it's a practical way to predict and optimize the daily cost of emergency rooms so that healthcare arrives on time.
To generate pseudo-random numbers, we use a linear congregation generator, or LCG. This is one of the oldest and most studied pseudo-random number generators, and it forms the foundation of our pipeline. The recurrence relation is x sub I plus 1 equals the quantity times x sub I plus c, all mod n. A equals 1,664,525, the multiplier. C equals 1,013,904,223, the increment. And n equals 2 to the power 32, the modulus which defines the space of all possible values. Starting from a seed x sub 0, an integer we choose. The generator produces a deterministic but statistically well-distributed sequence of integers. With our specific values, the form becomes x sub I plus 1 equals the quantity 1,664,525 times x sub I plus 1,013,904,223, all mod 4,294,967,296. To convert an integer x sub I into a number between 0 and 1, we simply divide by the modulus. Ri equals x sub I divided by m. This gives us Ri in the open interval from 0 to 1. These Ri values are approximately uniformly distributed on the interval 0 to 1. They carry no memory of the original integers. They look and behave like truly random draws from uniform 0-1 distribution. This normalization is in the bridge between the integer world of the LCG and the probability world or distribution. Now comes the key mathematical step, transforming a uniform random number into an exponentially distributed sample. We use the inverse transform method. The cumulative distribution function of the exponential distribution is f of x equals 1 minus e to the negative lambda x for x greater than or equal to 0. We set f of x equal to Ri, or uniform random number, and solve for x. This is the formula that converts each uniform value Ri into an exponential sample, Ni. It is fast, exact, and requires only one uniform random number per sample. Let me walk through the derivation explicitly so every step is clear. Step 1. Start with Ri equals 1 minus e to the negative lambda times Ni. Step 2. Rearrange e to the negative lambda times Ni equals 1 minus Ri. Step 3. Take the natural log of both sides. Negative lambda times Ni equals log of 1 minus Ri. Step 4. Divide both sides by negative lambda. Ni equals negative of 1 minus Ri divided by lambda. Step 5. Apply the simplification. Ni equals negative log or I divided by lambda. This is the final formula we implement in code. Putting it all together, seed x sub 0 goes into the LCG and produces x sub I. X sub I divided by m gives us Ri and negative log of Ri divided by lambda gives us our exponential sample. That is the complete pipeline. X sub I to Ri to Ni. 3 steps, 1 formula each, and we have a simulation ready in terrible time.
Hello, it's me again. For a simulation to be true to life, we must be able to transform digital noise into specific mathematical patterns. In this section, We will break down the code that allows us to create time intervals based on an exponential distribution. Every stochastic process requires a source. Here we define the LCG class, a deterministic algorithm that mimics randomness. We define the constructor dunder init, which takes a seed of time integer. Initializes the generator with a seed x sub 0, which we will define at the end, establishing the standard mathematical constants a, c, m that ensure a long cycle of numbers. Define the method next, which returns an integer. Executes the iteration to obtain the next integer in the sequence, updating the interval state. What is seed used for? The linear congruential generator formula is used in order to generate a sequence of pseudo-random integers within a range defined by my modules m. Large integers are difficult to process for probabilistic models. Therefore, we implement the function x of I to r of I to normalize the data. Return x of I divided by modules takes the integer generated by the LCG and divides it by the maximum possible value, m, converting it to a float. What is it for? The uniform transformation formula is used. It is used to obtain a number r of I in the interval 0 to 1, excluding 1, which represents a uniform probability as essential requirement for the next step. Now, we apply the magic of statistics with the exponential inverse transform function. This is where the flat number comes to follow an exponential distribution. If u is less than or equal to 0, set u equal to times 10 raised to the power of -10. A necessary mathematical safeguard, the logarithm of 0 doesn't exist, so we use an infinitesimal value. Return negative log of u divided by lambda applies the logarithmic function to obtain the final value of the variable. What is it for? The inverse transform method formula is used. It is used to map a uniform random variable onto an exponential distribution. It is essential for simulating waiting times or event durations where lambda is the occurrence rate. In data science, clarity is vital. The truncate to 5 decimal function ensures that our results are readable without altering the nature of the data through unnecessary rounding. Factor equals 100,000 defines the multiplier to shift the decimal points 5 places. Integer of value times factor divided by factor converts to an integer to remove excess decimals and then divides to return to the original scale. Finally, the generated exponential samples and print-fault table functions act as a conductor, executing the pipeline and presenting the results in a structured table for analysis. For I in range n, a loop that repeats the process 5,000 times. Generate, normalize, transform. Append to x of I list, append to r of I list, and append to n of I list, store each step of the data metamorphosis. Call the print-fault table function organizes the 5,000 records into aligned columns, showing the direct relationship between the raw value x of I and the final result n of I. The switch that sets everything in motion. The main block defines universal constants of our experiment. Z equals 42 sets their starting point for randomness. In a scientific documentary, reproducibility is low. With this said, any researcher will obtain exactly the same 5,000 results. Lambda equals 0.25 defines the intensity on the process, one variable every 4 minutes. Called the function generated exponential samples, triggers the chain reaction of all the previous functions, collecting the 3 states of the data: integer, uniform, and exponential. What is it for? The simulation parameter configuration is used. It is used to parameterize the simulation universe. It is the control center that allows us to change the speed of events or the sample size without touching the logical engine of the code. The code has finished its work. That became as an abstract system. The number 42 has blossomed into a data ecosystem that perfectly mimics the realm of reality.
Everything starts with C, the seed that begins the random number generator. This initial value is the starting point the algorithm used to browse the entire sequence of pseudo-random numbers. Xi can be any integer in this range. It can take any value between 0 and n-1, depending on the state of the generator. However, integer numbers are not very useful for simulation, so we divide Xa by n, transforming it into Ra, a decimal number between 0 and 1. This new value, Ra, behaves like a number drawn from a uniform distribution. This means that all values between 0 and 1 have the same probability of appearing. But we still need to convert this number into something useful for the simulation. Using a mathematical transformation, we convert Ra into Na, which represents the waiting time until the next patient arrives. In our model, each value of Na represents how many minutes pass before the next patient arrives at the hospital. The distribution we use depends on a parameter called lambda. The probability density functions describe how likely it's for the waiting time to take a specific value. In an exponential distribution, short waiting times are more likely than a long one. The cumulative distribution functions answer a different question. What is the probability that the next patient arrives before a certain time? Okay, to generate these waiting times, we first use a uniform random number between 0 and 1. Then we apply the inverse transform method using the formula x equals minus the natural logarithm of u divided by lambda. This transformation converts the uniform number into a value that follows the exponential distribution. When lambda is large, patients arrive more frequently. This results in shorter waiting times. When lambda is small, patients arrive less frequently. Waiting times between patients become longer. In our case, we use lambda equal to 0.25, producing an average waiting time of 4 minutes between patients. There is an important constraint. The value Ra can never be 0 because the logarithm of 0 is mathematically undefined. Additionally, the pseudo-random generator eventually repeats its sequence. However, its period is so large that it doesn't affect our simulation. The exponential distribution has a property called memorylessness. This means the probability of the next event doesn't depend on how long we have already waited. In this way, a simple seed number transfers into a sequence of realistic waiting times that allow us to simulate the behavior of a complex system.
Generating samples is only half the work. Before we can trust any results from our simulation, we need to verify visually and statistically that the samples we produced actually follow an exponential distribution. This panel contains 4 plots together. They form a complete visual audit of our pipeline. Top left, the PDF comparison. The blue bars are our empirical histogram built from the 1000 interval times generated by our pipeline. The red curve is the theoretical exponential PDF. Lambda times e to the negative lambda x with lambda equals to 0.25. Notice the shape, it starts at its maximum at 0. that is the mode and decays exponentially toward the right. This is the signature of the exponential distribution. The histogram closely follows the red curve. The fit is excellent. Top right. The CDF comparison. The greenest function is the empirical cumulative distribution function. We built it by sorting our 1000 samples and plotting the fractulation of values below each point. The red dashed curve is the theoretical CDF. 1 minus is to the negative lambda x, so the curves are nearly indistinguishable. That is exactly what we want to see. Pay attention to the yellow market. At x equals 4, f of 4 is approximately 0.632. This tells us that 63.2% of the generated interval times follow below 4 minutes. This matches the theoretical value of 1 minus e to the negative 1 equals to 0.6321. Bottom left, the uniformity check on RI. This plot asks a very specific question. Is our LCG actually producing well-distributed uniform values on interval 0, 1? The yellow dashed line marks to the expected density level of 1.0. What a perfect uniform 0, 1 distribution looks like. The shade band shows a plus or minus 10% tolerance zone. The histogram bars are approximately flat and stay within the tolerance band. This confirms our LCG is generate RI values that behave like true uniform random numbers. This step is critical if RI were not uniform. The exponential symbols downstream would also be incorrect. Bottom right, the QQ plot. QQ stands for quantile. This plot compares the quantiles of our 1000 generated samples against the theoretical quantities of an exponential distribution with lambda equals 0.25. If our samples truly follow that distribution, the points should fall along the red diagonal reference line and equals x. T2, the blue dots track the line closely from the smallest values all the way to the largest. There is a slight spread at the upper tail that is normal and expected with only 1000 samples. With 5000 samples, that tail distribution would be even smaller. 4 plots for independent checks: PDF, CDF, uniformity, and quantile fit. Every one of them confers the same conclusion. Our pipeline LCG uniform normalization inverse transform is working correctly. The 1000 samples we generate are statistically indistinguishable from true exponential 0.25 random variables.
Our samples have passed validation. Now comes the moment of truth. Do they behave realistically when we put them inside a system? Let's build an MM1 queue, the most fundamental model in queuing theory. The two M's indicate that both arrivals and service times follow memoryless distributions. That is to say, exponential when indicates a single server, a doctor, a care room. We take the first 200 ni values from the pipeline, the inter-arrival times with lambda equal to 0.25, and generate a second independent sequence for the service times with lambda equal to 0.333, equivalent to an average of 3 minutes per query. The utilization factor ρ, which is the arrival rate divided by the service rate, gives us 0.25 out of 0.333, approximately 75%. This means that the doctor will be busy 75% of the time, and since ρ is less than 1, the system is stable. The tail never grows indefinitely. MM1 theory tell us that with this row, the average wait time should be about 12 minutes, and the average number of the patients in the system should be about 3. Those are our reference points. Let's see what the simulation says. Now we will see the results with the graphs. The Gantt chart shows the first 30 patients. Each horizontal row is a patient. The orange segment is the time you waited sitting before being served. The green segment is the query time itself. Patient 1 arrives at minute 5.5 and finds the room empty, completely green bar, no wait. Patient 2 reaches 15 and still reaches the free doctor, a minimum orange bar of almost 2 minutes. But patient 3 reaches 17.4 when the doctor has only been with patient 2 for 2 minutes and will take 12 more. Patient 3 waits 3 minutes to receive only 1.8 minutes of consultation. The most striking case is the cluster of patient 8, 9, 10 and 11. The 8th patient arrives at minute 53.75 and enters directly, but patient 9 arrives just 0.54 minutes later. Patient 10 arrives at 0.02 minutes after 9, practically simultaneously. The 11 arrives at 0.64 minutes later for patient in less than 1.2 minutes. The result, patient 12 waits almost 10 minutes, 13 waits 9, 14 waits 8. A flurry of exponential arrivals created a queue that took 20 minutes to resolve. This graph shows the individual experience of the 200 patients. Each point represents a person. The 45 points exactly at 0, 22.5% of the total, are the lucky patients who arrived when the doctor was free. The highest point is patient 195, who waited 31.9 minutes. The dashed orange line marks the real average, 7.95 minutes. Notice the pattern in streaks, periods with high points followed by periods with points at 0. That is not random noise. It is the visual signature of exponential arrivals. When patient arrives in groups, waiting time increases. When there is a long gap, the queue empties and several consecutive patients enter without waiting. This green histogram validates the second pipeline. The service pipeline, the bars closely follow the theoretical red curve. The simulated average was about 3 minutes versus the theoretical average of about 3 minutes, a difference of less than 1%. Two independent pipelines, the same mechanisms but functioning currently at the same time. This is the complete systemic view. It shows how many patients are in the emergency room at any given time during the simulated 13 hours and few minutes. The step-like function increases with each arrival and decreases with each discharge. The queue reached a maximum of about 10 simultaneous patients. The system emptied completely 45 times throughout the day, and the average number of patients in the system was 3.11 compared to the theoretical MM1 value of 3.01. The model and the simulation match. The average system length 3.11 patients and service time 3.02 minutes, match almost perfectly with theory. The simulated average wait was 7.95 minutes, below the theoretical 12.05 expected with only 200 patients. What the equation cannot give us, the simulation can. Patient 195 waited 32 minutes. There were 45 moments of silence. That is what the exponential distribution produces when it becomes simulated reality. And our complete trip was: we started with the number 42. Throughout the linear congruential generator, the inverse transform and the exponential distribution. That number became 200 patients arriving, waiting and being attended during 13 hours in a simulator emergency room. The exponential distribution earned its place in this pipeline for 3 reasons. Its inverse has exact closed form, allowing a sample to be generated in a single calculation. Its memory list property accurately reflects how AR patient arrived, and a single parameter, lambda, controls the entry system. In short, pseudo-random numbers are the heartbeat of the simulation. Exponential distribution is one of its most fundamental voices, and now you know how it works.